Okay, I guess that's working. So what we're going to do is I'm going to first of all just show you my satellite station, and we'll talk about the different parts of that satellite station. Then we're going to look a little more technically at two concepts, namely mixers and Doppler, which I think are somewhat troubling on the extra exam. And then I'm going to go through the E2A01C questions, which pertain to satellite operation on the extra exam, and hopefully explain things and not just give the answer, but rather say why they are as they are. So when we start, we look up on my roof, and you see here my satellite antennas, and you can notice that there are crossed elements on 70 centimeters and also on 2 meters. And the reason that they're crossed is that if you cross elements at 90 degrees in space and then phase them 90 degrees apart, and that phasing is done with a phasing harness, and you can see some of the coax right here, so that as the elements are 90 degrees in space and 90 degrees in phase, then the result is that you have a circularly polarized signal. And we know that for example, if you put up a vertical and you would say you have vertical polarization, and if you put up a horizontal dipole, you'd have horizontal polarization. But a third option is that the waves actually spin as they go off the antenna, and that results in circular polarization. Our satellites are not circularly polarized; they're linearly polarized with just a vertical antenna. But the reason that we use circular polarization is that the satellites are not stabilized. They're just kind of lobbing and floating around. And if we didn't use circular polarization, we would see some deep fades in spin modulation as the satellites float around. And also there's a thing called Faraday rotation, which is the tendency of the polarization of a wave to change as it propagates through space. So we use, when possible, we use circular polarization on our antennas, and that tends to limit the fade as the satellite tumbles around. And it's mounted on a 5500 ASL rotor, which is what you see here. And this is a preamp that's located at the 440 antenna, and the voltage to power that preamp goes up the center of the coax. So that is pretty much what we're looking at as far as what's on the roof. So then we'll look at the station and talk a little more about what these different things do. And then we'll finally look at the screen of the computer and see what happens when we're actually working a satellite. We'll look at the radio in a little bit. This is an ICOM 821. It's an old satellite radio. It's about 35 years old. The reason I got this radio was back in the early 80s, AMSAT had a proposal to put up what they called Phase 4B. And Phase 4B was basically going to revolutionize ham radio. It was a satellite that was in what's called a Molniya orbit. And a Molniya orbit is a highly elliptical orbit that would always have its apogee or highest point over the northern hemisphere and the perigee over the southern hemisphere. And the apogee would go up to about 40,000 kilometers, which is the same altitude that geostationary satellites have. But it would not be geostationary. It would fling around and do about 2 of those orbits a day. So the first one they put up, something happened in the launch, and it ended up somewhere in the bottom of the Caribbean. And then the second one they put up, something happened with the transponders, and it never worked right. And after that, AMSAT fell into kind of a deep rut, and things didn't happen very much. And then about 6 or 7 years ago, I was at an AMSAT forum in Dayton, and thought, well, that's kind of fun. Maybe I can get back into it. So I energized this ICOM 821 and built a satellite station, and have had quite a bit of fun with that. But for now, the thing that I want you to notice is that the frequency dial on the right is the uplink. That's where I transmit. And notice that I'm transmitting on 435 megahertz. But the other thing you want to notice is that it's in lower sideband. And I'm receiving on 145 megahertz, and I'm receiving on upper sideband. We'll talk more about that in a little bit. And this mode is called UV, where U stands for UHF and V for VHF. So when we talk about the mode of a satellite, the first letter, which is a capital, represents the uplink band, in this case UHF. And the second letter, a small letter, represents the downlink band, which is VHF. There's also an L for 1.2 gig and an S for 2300, but those aren't used that much. We'll get into that a little bit later. But for now, let's look at the screen when I'm working a satellite, and let's look at everything that's going on the screen. This is a program called SatPC32, which is available on a trial version downloadable at AMSAT, and a registered version for AMSAT members, I think, costs $45. It did when I registered it. So what we're looking at here is a satellite XW2A. About the only thing that's available now are about 5 Chinese satellites, each of which have a bandpass of about 20 kilohertz. There isn't any good FM satellite that's available right now, so we're kind of limited. I think COVID has slowed things down a bit to the point where we don't have all the satellites up that we'd like. But now, if we continue to the right, you see the downlink frequency 145.677.809, and the uplink frequency 435.032. That means the satellite's operating in mode UV. Uplink frequency is UHF. Downlink frequency is VHF. The numbers below that represent the Doppler shift. Now, when the satellite is traveling toward us, and you can see here the position of the satellite, where the cross is, and my position is here. So as the satellite is traveling toward us, I have to receive on a higher frequency due to the apparent increase in frequency due to the Doppler. But I have to transmit on a lower frequency because the satellite wants to see the frequency correct. And notice that the Doppler shift on 2 meters is around 3 kilohertz at this point, and it can go up to about 9 or 10 kilohertz on 440. The Doppler shift is proportional to frequency. All right, so what's the computer doing? It's figuring out, first of all, where the satellite is. That's the X right here. Knowing the height of the satellite, it can then calculate the area of the Earth where the satellite can be seen above the horizon. And that's the highlighted area that you see here. So at this point here, I could work almost anybody in Canada and in part of the northern part of the US. And these dots represent where the satellite will be every two minutes. The solid line is called the terminator. That's the distinction between daylight and darkness. The S right here represents the point at which the sun is directly overhead. So by looking at the satellite here, we can see that it is going south, which implies that it is a descending orbit. We get descending orbits at one point, and then about 12 hours later, we get ascending orbits. All right, up here it says the satellite is in the sun, and this is giving me the time and date. These corrections here are kind of like a receiver or transmitter incremental tuning. So if I want to clarify a signal, I can do it in 20 hertz steps here, 100 hertz steps, 500 hertz steps here, and so on. All right, let's continue down here. Since this computer knows where the satellite is, it can then determine the azimuth and elevation of the satellite. I want to go back just a little bit and look more at the station here before we go on. Next to the radio, we have an LVP tracker. This tracker was designed by, sorry about the phone. This tracker was designed by Mike Young, if you know him, WB8CXL. a former student at Akron U. He designed this tracker and sells it through AMSAT. The purpose of the tracker is to take information from the computer as to the azimuth and elevation of the satellite, convert that digital information into an analog voltage, put that analog voltage at the back of the rotor controller so that it is automatically then adjusted so that the antennas are always pointing toward the satellite. So what's the computer doing then? It's determining where the satellite is. It's sending a digital signal to the LVB tracker, and that is then sending a signal to the antenna controller and pointing the antennas. The computer also is determining the Doppler shift, and that Doppler shift then is sent to the radio so that the radio is continuously adjusting its frequency for Doppler. Now, how does it do that? Well, one of the numbers at the bottom of the screen is the range. That is, the computer is determining how far away the satellite is from us. And knowing how far away it is from us now and how far away it was from us a certain time ago allows it to calculate the velocity at which the satellite is approaching us. Knowing the velocity at which the satellite is approaching us and the frequencies that we're on, it can calculate the amount of Doppler shift. The number that you see here, this 2.809, is the amount of frequency that I have to add to my nominal frequency when I receive. And this minus 8.389 is the kilohertz, the number of kilohertz that I have to subtract from my nominal frequency when I transmit. And those numbers are always changing due to the Doppler and the fact that the range is constantly changing. Once the satellite passes and starts going away from us, then this number will be negative, because as the satellite's going away from us, then I'm going to have to transmit on a higher frequency, because the satellite's going to see the lower frequency, and I'm going to have to receive on a lower frequency. This is all taken care of, automatically sent to the radio. And the third thing that the computer might be doing is, if I am operating some kind of a digital mode, it's operating as a software TNC, a terminal node controller, changing the ASCII into tones and vice versa for digital transmissions. All right, so what else can we look at here? At this point here, the azimuth is 345 and the elevation is 2.7 degrees. The number all the way to the right, the max elevation, that's telling me how high above the horizon the satellite will be on this particular pass. When we look on this MA, that's mean anomaly. That's not too interesting in these satellites because they're close to a circular orbit. But the mean anomaly basically starts at 0, goes to 256 as it goes from perigee to perigee. Now, then how does the computer know where the satellite is? And the way it knows where the satellite is because there's a file that has loaded what are known as Keplerian elements. Back in the 1700s, there was a genius astronomer and mathematician in Vienna, Austria, whose name was Johann Kepler. Kepler believed that the planets orbited the sun in circular orbits. And he set about to prove that. And to do that, he calculated where Mars should be as a function of time. Now you're in the 1700s, no calculators, no computers. He's running all the numbers by hand. He and another person then observed where Mars was as a function of time and compared that with his calculations. And when he did that, he found they were pretty close, but not exact. So what to do? Well, option one, say, well, close enough, throw in a fudge factor, everything's proven. That's what I'd do. But Kepler had a different approach, and he said, the numbers don't exactly match my computations. Maybe there's something I really don't understand. He studied more and found that, in fact, the planets orbit the sun in elliptical orbits, with the sun at one of the focal points of the ellipse. And he then formulated 3 laws of orbital motion, which are basic and form the fundamentals of what we know today. So in honor of Kepler, we have established what are called Keplerian elements. There are 7 of them, and they have strange names, right? Ascension of ascending node, eccentricity, and things like that. But you don't have to know what the 7 are, but just know that if you know what these 7 Keplerian elements are, then you can show where the satellite is, where it was, and where it will be. And there's a file that the satellite SAT-PC32 references, so that when you put up a new satellite, then you have to modify that file and load the Keplerian elements into that file. The computer then uses those elements to determine where the satellite is. And NASA continuously tracks tens of thousands of things in orbit around the Earth, mostly space junk, burnout, second stage boosters, things like that. But these NASA updates a file showing where the Keplerian elements are. And if you look all the way down to the bottom of the screen, which you might not be able to see, it says CAPS NASA all 10/9/2021. And that's showing the last time that I updated the Keplerian elements. And one of the tabs here, when you click on tracking, one of the tabs says update CAPS, and you click on that, and it grabs them off the internet, updates all the CAPS. Let's see, what else do we need to know? The height. So this shows how high the satellite is, 444 kilometers. Satellites that we use now are all in low Earth orbit, and low Earth orbit is somewhere 400 to 600 kilometers. The space station is about 400 kilometers. So this is almost as low as the space station. One of the reasons that we put these satellites in such a low Earth orbit is that we're not allowed to keep them up forever. We have to prove that this satellite will destroy itself in 30 years. And by putting a satellite up this low, every time the satellite gets hit by a molecule of air, it slows down. When it slows down, it drops into a lower orbit. Eventually, it drops into an orbit that's so low that it burns up on reentry. What else? Range we did. Longitude and latitude. Now, just for ease, of course, we know that we are at a longitude of about 80 degrees west, but we often refer to the longitude as right ascending from the prime meridian. So we don't have to deal with negative numbers. So if you look at the longitude here, it says 270, but that's 270 degrees east of the prime meridian. And then the 59 degrees represents the latitude. Orbit number, this satellite has gone around the world 34,228 times. And this is showing the time at which we'll lose signal. LOS will be at 1210. The AOS is blanked out because we're already in acquisition. Before that, it would have shown the time of acquisition and the time of loss. Any questions on anything I did there? That's maybe kind of fast. That makes sense? Okay, moving on then. Right now, we don't really have any good FM satellites up. The satellites that are up are primarily 5 Chinese linear satellites. But what I like to do is travel to different places and work satellites from a portable location. Now, when I did a satellite presentation for you guys several years ago, I took this same setup here out into the parking lot. There was a satellite that went over, and I made several contacts through the FM satellite. Here I am, Tom KP2E, and a couple other guys, and I went up to northern Manitoba on a polar bear expedition. And I got a lot of people excited because Churchill, Manitoba had never been activated in that grid square. So here I am working satellites through from Churchill, Manitoba, and keeping an eye out for polar bears who were wandering around the town at the time, and making quite a few contacts. Now, let's think about Doppler, though, because now I don't have any computer to control it. I have one hand to hold the radio, one hand to hold the antenna, and I need a third hand to do the logging. I only have two. So the way I would handle the logging is I would use a digital recorder on my phone. And when the satellite came over, then I would just record all the contacts that I made and then write them down after I finished that. But how do you handle Doppler? Now we're on FM, and most of the satellites now are mode UV. That means I transmit on UHF and receive on VHF, which in a way is kind of unfortunate. There was a real workhorse satellite that the Saudis put up, SO50, which transmitted VU. And that was a lot handier because if you transmit on VHF, you don't really have to worry about Doppler because the Doppler is not going to shift more than 3 kilohertz. And 3 kilohertz on FM is not a problem. But it's going to shift about 9 kilohertz on UHF, and that is a problem. So if the satellite was operating on mode VU, I'm receiving it on UHF. And I keep my transmit frequency constant. And if the receive frequency gets a little fuzzy, then I just change it. I'd program 5 different channels into the HT, representing the AOS and then approaching and then overhead and then departing and finally LOS. So I would just change it. Well, you can't do that if you're in mode VU, because if you're in mode UV, because you're receiving on VHF and it's going to sound fine, but you're not receiving your own signal. So when you're operating mode UV, which is where most of the satellites are, you have to kind of plan ahead and say, well, I'm going to be in channel 1 for the first 5 minutes, and then 6 and 7 I'll be in 2, and then 3, and then kind of guess that way. But anyway, it works. And what I did a lot of times before COVID came along is in the winter, we would go down to some island in the Caribbean, get a license, and I was able to work back into the States and create kind of a mini pilot. But that's not possible now because we don't have any good satellites up that operate on FM. If you want to know what a satellite looks like, here's an example, and you can see by this man's hand the size of it. This is what we call a 1U satellite. A 1U satellite is 1 unit, and a unit is defined as a cube that's 10 centimeters on an edge. For the metrically disabled, that's about 4 inches on an edge. So basically, these satellites have roughly about the same volume as a softball. So we have to put into that, of course, there's solar panels on all faces of the satellite, and we have to put in the transponder, the receiver, the transmitter, and some way of transmitting the received signal. Okay, so there's 2 different types of satellites. The nonlinear satellite, which is used for FM, is pretty simple. It has, if it's operating on mode UV, it has a 70 centimeter antenna, an FM receiver, extract the audio from the FM receiver, put it into an FM transmitter, and then transmit it. It's basically a crossband repeater in the sky. So that's what an FM satellite is. But on a linear satellite, and we're going to talk about this a little more technically, it receives the signal, again, mode UV, it receives a 70 centimeter signal, amplifies it, and then puts it into a mixer. And I'm going to talk about mixers in a bit. And that mixer basically converts the 435 signal down to 125 megahertz signal, which we then filter and amplify and transmit. All right, now we're coming into one of the problems that I had on the extra class test. So we're going to spend a little bit of time talking about mixers. And I chose the satellite CAS-4B, which is one of the Chinese satellites. And if you look at this, it has an uplink. It's mode UV. So it has an uplink on 435.27 to 435.29, so 20 kilohertz passband, and downlink on 145.915 to 145.935. Now, if I take the center frequencies, then you have 435.280 and 145.925, and I look at the sum of those center frequencies, 581.205, and the difference 289.355. So now we're going to look at a mixer, and a mixer, an unbalanced mixer, is a device that takes in 2 frequencies and puts out 4. And the 4 frequencies that it puts out are the 2 that were put in, and the sum and the difference. What we're after here is a question that I believe is wrong on the extra class exam, and I'm going to show why. So if we look at this now, and first of all, I'll use the difference frequency, that's 289.355, and I'm going to put that in to a terminal that we'll call a local oscillator or intermediate frequency. And then up here is the input frequency, the UHF frequency, 435.28. So what comes out? The 2 frequencies that I put in, 435.28 and 289.355, and their sum, 724.635, and their difference, 145.925. And we notice these 4 frequencies that come out. The only one of which I have any interest is the 145.925, because that's the 2-meter signal. So I put that into a filter, and I get out the 145.925. So this is a scheme then of converting the 435.280 into a 145.925. Well, that's what we want. Now, then the question is this an inverting or a non-inverting passband? So on a non-inverting passband, as you raise the input frequency, the output frequency raises. And on an inverting passband, as you raise the input frequency, the output frequency decreases. Well, let's find out. We'll raise the input frequency by 5 kilohertz. So now I put in 435.285. And the sum of the frequencies that I get out are, again, the sum and the difference. And what I get out is a 145.930. And we notice that that frequency is 5 kilohertz higher than the frequency that I put in. So if I use the difference of the center frequencies as my local oscillator, then this transponder becomes a non-inverting transponder. That is, when you raise the input frequency, the output frequency raises. Remember, one of the first things that I showed you was my transceiver, and I showed you that when I transmitted on lower sideband, I received on upper sideband. That implies that I'm going to need a inverting passband. Okay, so now let's look at the inverting passband. Now, here, I'm going to use the sum of those 2 frequencies as my intermediate frequency or local oscillator. Sorry. When I do that, again, I get out 4 frequencies, and I filter everything out except the 2-meter signal, which is 145.925. Now the question is that inverting or non-inverting? So again, I raise the input frequency by 5 kilohertz, and I look at the output frequencies, ignoring everything except the 2-meter frequency, and I see that that's 145.920. So in this case, as I raised the input frequency by 5 kilohertz, the output frequency decreased by 5 kilohertz, implying that I now have an inverting passband. Now, let's pause for a little bit and go back more to the basics and look at modulation review, because we have to explain why, when I transmit on lower sideband, I have to receive on upper sideband. If we go back to traditional AM, we have a carrier, an upper sideband, and a lower sideband. And the power in the upper sideband and the lower sideband is m squared times the power in the carrier over 4, where m is a modulation index, anywhere from 0 to 1. So at 100% modulation, I'd have at a 1,000-watt carrier, the upper and the lower sideband would each have 250 watts, or there would be 100 or 1,500 watts going off the antenna. But if I reduce the modulation to 0.5, now the upper and the lower sideband now go down by a factor of 4, so there's only 62.5 watts. So we see that at a modulation of 1, I'd have 1,500 watts going off the antenna, but at a modulation of 0.5, I'd have 1125. All right, frequency domain. What comes out of the speaker of a receiver is then the amplitude of what comes out of the speaker of the receiver is represented by the amplitude of whatever is in these sidebands. And the sidebands are mirror images of each other, so each one contains all the information that you need. And the frequency that comes out of the speaker is a difference in the frequency of what's in the sideband and the carrier that you transmit. But it takes a lot of power. So what would happen? First of all, I don't need both sidebands. Each one of them contains all the information. So if I suppress one sideband and the carrier, what I would have then is this. I still have all the amplitude information I need, but I lost my frequency. So what I do then is insert a tone at the receiver at the point where I think the carrier would have been transmitted if it had been, but it wasn't. And we call that a BFO. We don't know exactly where it is, but we turn around until things sound normal. And at that point, I can receive a signal. But notice that the power in the transmitter from AM went from 1,125 watts down to 62 watts, and you still have the same information. So obviously, single sideband is a lot more efficient. But since the sidebands are mirror images of each other, and if I have an inverting passband, as you increase one frequency, the other decreases. So if I transmit on the lower sideband, I'm going to receive on the upper sideband because everything gets turned around backwards. So that creates then a problem with one of the questions on the extra exam. And I'm going to go over these at the end, but I want to look at one right now. This question says, how is the signal inverted by an inverting linear transponder? And that's what I've exactly been talking about. And the four answers are, the signal is detected and remodulated on the reverse sideband. The signal is passed through a nonlinear filter. The signal is reduced to I and Q components. So the Q component is filtered out. And the signal is passed through a mixer, and the difference rather than the sum is transmitted. Now, which of those four answers is correct? And the answer is none of them. They're all wrong. Because it doesn't have to do with the difference rather than the sum being transmitted. If you are transmitting through a satellite that is in mode UV, you're changing a UHF frequency to a VHF frequency. That means you're changing a high frequency to a low frequency. Well, if you're changing a high frequency to a low frequency, it has to be a difference. You can't get a low frequency from some. And I'm not sure if the person who put that in didn't understand mixers. I mean, the correct answer is the sum of the two frequencies is used as the local oscillator, and the resultant is an inverting passband. Well, you would have passed the test, you answered D, but it's not correct. Anyway, that's the one problem that I had. Now, the second problem I had dealt with Doppler. And if we look at question 2, it says, which of the following occurs when a satellite's using an inverting linear transponder? And the first part bothers me. Doppler shift is reduced because the uplink and the downlink shifts are in opposite direction. When I went to an AMSAT forum some years ago, I asked the same question and got the same answer. But it bothered me for two reasons. Number one, who cares what the Doppler is? The computer's going to figure it out. And two, that might work okay if the satellite's approaching you, but it seems that as the satellite's going away from you, it'll have the opposite effect. In other words, do you really get a reduction in Doppler shift because the uplink and downlink shifts are in opposite direction? And the answer is yes, half the time. But in the other half of the time, I think you get an increase. But I haven't proven that. So I set aside to prove it. I did it the following way. Let's suppose that we have we're transmitting through a satellite that's inverting in mode UV, and we put a 1 kilohertz tone into the microphone. So if you put a 1 kilohertz tone into the microphone, you would like to have a 1 kilohertz tone out of the receiver. All right, now let's then assume that the Doppler shift on UHF is plus or minus 9 kilohertz, and on VHF it's plus or minus 3 kilohertz. So is the satellite, and we're going to transmit on lower sideband. So as the satellite is coming toward us, it's approaching us, the transmitting frequency would be the carrier or nominal frequency, minus 9 because we have to transmit lower, minus 1 because we're on lower sideband. So that would be the carrier frequency minus 10 kilohertz. And I would receive that on, now I'm receiving on upper sideband, so I'd receive it on the carrier frequency of plus 3 plus 1. And when I did that, I would see that the total shift in the transmit and receive frequencies would be 14 kilohertz. Okay, now let's suppose the satellite's going away. If I transmit, I would be on a carrier frequency plus 9, minus 1, again, I'm on lower sideband. I would receive it on the carrier frequency minus 3 plus 1, and the total shift on those two would be 10 kilohertz. Well, that's nice. Satellites overhead, there's no Doppler. Okay, but so what did that get us? It got us, with an inverting passband, it made things worse as the satellite's approaching us, and better as it's going away. Now, what would happen if I had a non-inverting passband? So now I better transmit on lower sideband and also receive on lower sideband. All right, here the transmitting frequency would be, as before, the carrier frequency minus 9 minus 1, or carrier frequency minus 10. Receive frequency would be the receive frequency plus 3 minus 1, or the carrier frequency plus 2, and the total difference would be 12 kilohertz. And as it's going away, it's still 12 kilohertz. So that inverting passband, that didn't fly. In other words, you can't use that to explain why you use an inverting passband. Now, if you used a non-inverting passband, you'd get 12 kilohertz of total Doppler in both directions, and the other way you get the 10 one way and 14 the other. Doesn't matter, it still averages out to 10. So I don't like that answer. So if that's the case, then half the satellites ought to be inverting and half of them ought to be non-inverting, because Doppler doesn't matter. But they aren't, they're all inverting. So if they're all inverting, what else can we attribute that to? Why are the satellites inverting? So let's go back then to our discussion on mixers. And let's look at the frequencies that were involved with a non-inverting and an inverting mixer. Now, if you look at those two frequencies, and suppose you're an engineer and you want to design that filter, which one would you choose? Well, if you look at the non-inverting, you see that you have one frequency that's just twice the frequency of the 2-meter signal that you want. And if you look at the inverting passband, you see it's 3 times the signal that you want. So it kind of makes sense that for filter design, you would use an inverting passband just because the filter is cheaper and easier to build. Well, that's my 2 takes on it. I'm open to any discussion on that, but I don't buy the Doppler shift and the inverting linear transponder. That's just wrong, but that's nothing more that we can do about that. What I kind of want to do now is, I think with what I've done so far, kind of answered all the questions, but we can go through each of the questions on the extra exam and be sure that we've got everything taken care of. Let's see, I can stop share and okay, we are. Let's look at each one of those and be sure that we have those understood, because I think I covered most of them. Direction of an ascending pass. Ascending pass is then a pass of the satellite which is going north. and a descending pass is going south. And we also sometimes talk about a node, and a node is where the satellite crosses the equator. So we can talk about an ascending node and a descending node, and that would be the point in time at which the satellite is crossing the equator going north or south. Inverting linear transponder, I already talked about that. I don't like the answer on Doppler, but the signal position in the band is reversed. That's correct. Upper sideband becomes lower sideband, vice versa. That's correct. Doppler, I have my doubts. How is the signal inverted? We talked about that. All those answers are wrong. The correct answer is that you put the sum frequencies in as the local oscillator, and the signals are inverted. Mode, I talked about mode. That has to do with the frequency bands where you're operating, where V is VHF, U is UHF, and then L is 1.2 gigs and S is 2.3. Letters in a mode, what do they signify? Just said that. The frequency band that we're talking about. Keplerian elements, I talked about that. Types of signals that can be relayed through a linear transponder. Linear just means linear. Whatever you put in, you get out. Possible to do. Can you put an FM signal through a linear transponder? Yes, you can do it, but no, you won't make any friends, because that satellite, that one signal is going to grab all of the power of that transponder. So you might get your tires slashed, but yeah, you can do it technically, but it's not done. Why should effective radiated power to a satellite that uses a linear transponder be limited? This satellite is sitting up there, and it's putting out about 1/4 of a watt. And that 1/4 of a watt has to be divided up among everybody that's using it. So the more people that use it, the less amount of power that's available to each one. And if somebody is really blasting that with high power, he can suck up the power of the whole satellite. Back last time, I took the satellite station out and operated field day for you guys, and there was a satellite pass coming up like about 10:30. I thought, well, it's going to be great, but there were a couple other lower satellite passes lower on the horizon, and I got on those and worked several stations. Well, then when the satellite went right overhead, I tried to get on. I was finally able to make one contact. There were so many people trying to use it that there was so little power available to everybody that I had a tough time making any connections. So the idea is you want to use the minimum power necessary so that everybody else will have a chance to use a satellite and will have sufficient amount of power. L and S, I talked about that, 23 and 13 centimeters. Satellites that appear to stay in one position in the sky. The answer there is geostationary. We don't have any ham geostationary satellites. However, the Saudis put one up, and it's parked over Europe. And the Europeans have a geostationary satellite. It's called nickel-dime. It's 5 gigahertz up and 10 gigahertz down, but it has a very wide bandpass. And you don't have to track it with Doppler because it's stationary at one point in the sky. And they can actually use like a dish antenna, and they can and track it. And you put your up and down converters right at the parabolic antenna, because you can't take the loss at 5 and 10 gigahertz. Well, too bad for us. We can't use it, but they can in Europe. Okay, the type of antenna to minimize effects of spin modulation and Faraday rotation. I talked about that at the beginning. You saw that I had a circularly polarized antenna. They talk about digital store and forward functions on an amateur satellite. We don't have any now, but we kind of do with the International Space Station, because the International Space Station usually has an APRS function, and you can APRS through the International Space Station at their frequency, which is 145.825. But you can use the message portion of an APRS signal to form a Q cell, and I've done that just to see if it works. So you can say put a CQ in the message part of an APRS signal, and then somebody else can answer you, and you can get a signal that way. What else? The techniques are mainly used by orbiting digital satellites, and again, that's store and forward. If you want to have a conversation with somebody in New Zealand on the satellites, you can't reach them on the satellites, but you could put a message onto store and forward, which they could then download and answer, and you could carry on a communication that way. That covers all of the questions on the test, and nobody can get too technical, but I'm open to any questions that anybody has.
Mel, have you contacted the NCVEC and complained about their questions?
I'm not sure why those mistakes occur. I know it's a generally accepted fact that Doppler is reduced when you have an inverting passband, but I don't believe things I can't prove, and I can't prove that. In fact, I can prove that if you have an inverting passband, it'll change from 10 to 14 kilohertz, and a non-inverting, it'll stay at 12. And the other thing about the transponder, I think what I went into is probably more in detail than what most people would want to encounter. I'll leave that up to you. I mean, I've showed mathematically in both cases where the problem is. And I think it's kind of obvious, but I mean, it's so obvious that if you're in mode UV, you're converting a UHF signal to a VHF signal. Well, of course, you're going to do that with a difference. You can't get a difference from a sum. But that has nothing to do with whether or not the signal is inverted or not. That has to do with what you're using as a local oscillator to form that conversion. Well, yeah, but would they put that on the test? If they put it on the test, how many people could understand it? I don't know. I'll leave that up to you.
Well, I would say they shouldn't put it on the test.
Yeah, they shouldn't, but I think it's
wisdom
important.
is wrong. It should not be on the test.
Yeah, I agree, and I think you can see that it is wrong. Option one is just leave it off the test because it's more complex than what the test should encompass. I don't know. You're more involved in testing than I am, so leave that up to you. So, anything else that we can talk about in terms of satellites that I didn't cover or didn't cover well enough?
Do you want to tell your polar bear story in Churchill?
Oh yeah, well, so I was in Churchill, and we went up in November, and Tom Price, KP2E, and I and a couple of guys went up, and I was really making a lot of contacts because it was the new grid square for everybody, and but I'm in northern Canada in November, so it's cold and snowy, and I got up, and there was this satellite pass coming over like 7:30 in the morning. Well, the sun didn't rise until about 10:30. It was dark and it was snowy and it was cold, and I said, "Oh heck, forget it, I'm not going out." So later on, then we went to breakfast, and this guy said, "Hey, you guys hear that polar bear? It was about 2 doors down from where you are." So I lucked out by not trying to work that pass. I might have had to encounter a polar bear had I done it. Still worked a lot of stations.
Mel?
Yes.
This is Jim, WA3JAT. One thing I think maybe you might talk a little bit about is for people who don't have the directional antennas with the elevation and azimuth, what they might use for antennas. I've got one here that I built from a kit. This is a turnstile antenna. I don't know if I can get the camera back far enough that you can see it.
Yeah, those are good, and I've also used egg beater antennas. If you guys have come out to field day when I've worked satellites for you guys, I use a pair of egg beater antennas because they look like egg beaters, and they basically transmit circular polarization without gain. They work really well at the field day site. and I work a lot of stations for you guys. I had them on the roof of the house and they don't work that well. And the reason is without any gain, I've got a lot of trees and I try to shoot those signals through the trees without any gain, and it just doesn't work that well. Get out in an open field and it's great. And it's amazing on those egg beater antennas that I'm working stations when the satellite is like 10 degrees off the horizon. You think it'd be straight overhead, but you get out into an open field and put those egg beater antennas on, they work great. But on top of the house, it was kind of marginal. The antenna that you saw me working with the FM handheld is called an Arrow antenna, ARROW. They cost about $150, and they will be great when we get some more FM satellites up. The problem that you have with the FM satellite is it's basically a crossband repeater in the sky, which means that only one person can use it at a time. And as more and more people get to it, and most of you already have the equipment that you need, it's just a dual band HT. So you already have the radio and using some kind of an antenna, and there are designs on amsat.org that showed how to build one, or you can buy one for $150 and then you're on the satellites. But it's there's so many people that now are getting on satellites, especially FM, that it's becoming kind of difficult to make contacts. When I'm in the Caribbean, then I can wait and I can see where the pass is coming up and when it's just going to hit the U.S. And of course, a lot of people want to contact me. So when I'm in the Caribbean, I'm working back into the States, but I'm establishing myself first as on an ascending pass, and then that works. But just to get on and make a contact with an HT, like I did for you guys several years ago, can you do it? Yeah, but it's kind of iffy because it only takes one station on FM, the highest powered, loudest signal captures the passband. It only takes one station with more than you to capture the satellite, and you're standing there with a 5-watt HT and a handheld antenna. It works, but it's kind of difficult.
Yeah, there's one other antenna that I would mention too. The Elk makes a log periodic that's 440 and 2 meters. And even though it's not circularly polarized, I've had some success with that portable as well.
Yeah, I'm using this. Those are the ones that you saw on the roof are Cushcraft. It's called an LEO pack, and for low Earth orbit pack. And and of course with the handheld, you're not circularly polarized either. The circular polarization helps in spin modulation, but it's not necessary. You can still get a good signal with things that are linear. So on that log periodic though, but the log periodic covers 2 and 440?
Yeah, Elk makes it, and it's got a handle at the end, so it's easy to point at the satellites. It's a little bit smaller than the one that you used at our demonstration at our club. So it's a little bit easier to handle in the field for that reason.
Okay. Yeah, there are a variety of things out there, and I've had good luck with that Arrow antenna, but there are many other things that work as well. Okay. Any other suggestions, questions, comments? Okay, well, I hope I didn't muddy the water.